Okay, something I do want to mention, and this is where we have from the method of least squares. I'm looking at also including what is regarded as the sum of squared error. And let's say that for just determining the equation of the line of best fit, and say you have three ordered pairs involved. Okay, we have the origin 1, 1 and 2, 4, and looking at the line of best fit. So in establishing our matrices for x and y, so we have for x, the first column you have to consist of 1 exclusively. Second column you have the x coordinates, we have 0, 1, and 2. And for y, we have again a one column array of just the y values from the ordered pairs. And taking the transpose of x times x, multiplying together, okay, we have the top row with 3 and 3, and the bottom row we have 3 and 5. After the attainment of that product, we're looking at that particular inverse of the result, and the inverse of the product of the transpose of x and x, we have this array of fractions. Looking at the product of the transpose of x with y, and we have for that result we have the one column with the two elements 5 and 9, and looking at taking the product of what we have with the inverse of the transpose of x times x and what we have with the transpose of x times y, and we have with the numbers we have negative 1/3 and 2, and we have negative 1/3 in reference to a naught, 2 with respect to a sub 1, and we have in terms of the line of best fit, so we have y is equal to negative 1/3 plus 2x, or in slope intercept form we have y is equal to 2x minus 1/3. And if you notice in this graph, okay, we have the line, okay, misses all three of these points, and this is regarded as the line of best fit. And looking at what is regarded as the sum of this error squared, okay, so we have for our assigned y values, okay, again we have 0, 1, 4, and for what we have in the case of the function value, where we have f of x or y is equal to 2x minus 1/3, okay, and for what we have theoretically whenever we have x, again, which was at 0 from the origin, your theoretical y value comes out to negative 1/3, and for x equal to 1 from the second point, okay, we have 5/3, and if you notice we have so far for the amount of error, okay, from the first point you have the actual recorded y at 0, theoretical at negative 1/3, so you have 0 minus 1/3 is equal to positive 1/3. For the second we have 1 minus 5/3, which comes out to negative 2/3. And for what we have from the third point, okay, we had x was at 2 and the actual y value was at 4, and for the theoretical y value f of x of 3, which is f of 2, that is equal to 11/3. And for the amount of error we have, in this case we have 4 minus 11/3, which comes out to positive 1/3. And for taking the error amounts and establishing a one column matrix, we had the transpose, okay, to end up as the one row matrix where we have 1/3, negative 2/3, and 1/3. And for the sum of the squared error, okay, we have the product of the transpose of E times E, and this comes out to 2/3. So 2/3 will be the sum of the squared error. And also just a second case here, so we have 5 distinct points, and going through the cycles, and we have with the products of what we have involved, okay, for the transpose of x times x, so you have 5, 27, 27 and 2 of 5, and the inverse of that results, okay, we have with this set of fractions where we have these numbers involved. And for the transpose of x times what we have in the set of y values, so that result we have was 0 and negative 70, and taking the product of the aforementioned inverse and multiplying by what we have in the product with the transpose of x times y. Okay, and we have with our coefficients, so we have a naught is equal to 945 over 148. A sub 1 we have at negative 175 over 148, and we have this resulting linear equation. And for what we have in the graph, okay, now we have this result to be the line of best fit. Now it's not passing through any of the points, but now there can be some situations where a line of best fit can run through some of the ordered pairs. Okay, and for what we have here, this graph represents the line of best fit, and that is to minimize, okay, the collective error amount. And for what we have in the case of the determination of the sum of the squared error, so we have with the recorded y values of 630, negative 4, and negative 5. Again, 630, negative 4, negative 5, and taking f of x sub n and inserting the equation that we have attained defining the line of best fit as we enter the x values from earlier. Okay, you do have a difference between what we have with the actual y and each of the recorded theoretical outputs. Okay, and so you have some of the error amounts are negatives, others are going to result as positives, and going through what we have here with the error amounts. So we have one column matrix. Taking the transpose of that layout, we have a one row result, and for the sum of the squared error, taking the product of the transpose of E with E, and the sum of the squared error comes out to 239 over 74. Again, the problem was finding the sum of the squared error, but now in terms of the sum of the error, you're going to have the positive and the negative error amounts to cancel each other, so the sum of the error will be 0, like in the first case, and also we have with the second case. So the sum of the error is 0, while you have the sum of the squared error to be non-negligible.